properties are the main reason. The main point here is robots using ground for their locomotion are known as mobile robots. There are numerous types of mobile robots. Main are three: wheel types, legged robots, and tracked robots. Leg robots are basically humanoid robots that have legs like humans. Tracked robots, tracked meaning there is a track around their wheels. And you can take an example of a tank, the army tank, the fighter tank, that has a specific track around its wheel, and that is rotated with the help of motors, obviously, and the robot moves. The third type that we will be utilizing and going in deep detail of it is the wheel type. Although the name is a little bit confusing, but wheel types robots are very interesting and beginners friendly because in leg they have a lot of kinematic stuff. Tracked, they also have a little bit complex than wheel types. In wheel types, we have different types of wheels to be dealing with. First, the standard wheels, the wheels that can only rotate in forward or reverse direction. Okay, that we will be using in this course because it is a basic course. Orientable wheels, you might have seen these type of wheels in trolleys. They can rotate forward and reverse with this motion and also this axis of rotation as well along Z axis. So basically they have two axes of rotations, which is very useful. The ball wheels, they can rotate on X, Y, and Z, all of these axes. Okay, but only the ball can rotate, and we cannot attach direct motor to it as we can attach to standard wheels. Now comes the Omni wheels and Magnum wheels. These wheels are very interesting because of their ability to move in all possible direction in a certain arrangement for the robot. This might be confusing, but you can check Google, and I will be utilizing them in the future advanced courses as they have a little bit complex mathematical equations to solve. So what are the robots we are going to be using in this course? The first one is going to be the dolly robot, and the second one is going to be what I call is rover. I don't know the name is a good representation or not, but the thing is it has four wheels, some sensors on it, and that's why I call it a rover. This dolly is utilizing this ball, front caster wheel, and standard wheels at the back. The rover is utilizing standard wheels on all 4 points where the wheels are. Both of these robots have different mechanisms. What we define in the field of robotics, the first one is a great example of differential type robot. But the second one is also a differential type robot, but it is more defined in its kind, and that is skid steering, which is actually meaning that if these two tire number 1 and 2 are rotating in this direction, making the robot move in this direction from this side, the wheels 3 and 4 needs to rotate in the opposite direction to make that side move in the reverse direction, and then the robot is going to be able to take a turn. This process is also known as differential type robot because this whole process is also being implemented in this robot. One wheel rotates in one direction, the other rotates in the opposite, and the robot turns. But the point here is this causes the robot to skid from one side of the wheel and also on the other side of the wheels as well, which causes the steering of the robot. That's why it is known as the skid steering robot. The next robot, the very interesting one we are going to be using is Prius hybrid. Although I should say that it is a car, it is not a robot, but in a sense we are utilizing it to follow certain commands that mostly robots do, and there is no passenger, so I will be calling it mobile robot. Now, the mechanism driving for this car is known as very popular Ackerman drive. I am telling you the driving mechanisms of these robots because you can search a lot of research papers, and these jargons of robotics can make now sense to you if you read some text, and you will understand what they are talking about. In Ackerman drive, you have front wheels, and in those front wheels we have an axle. That axle can be rotated at a specific point along the Z axis. The blue line here is representing the Z axis, which causes the wheels to take a turn. Okay, so this is the basic working of Ackerman. We will be utilizing this previous hybrid gazebo pre-made model. You don't have to make it and make it do some awesome stuff. Let's first understand how our project is completed in ROS. If the project is robot based, we have to develop a robot. If we are not just trying the algorithm, we are making a robot, actual robot, we need to first create a URDF. You can say that URDF is the robot for the simulation, just that. If you have gone through this URDF programming, and we will be going through in this course, and you will understand more about the URDF. First, we create a robot with the help of URDF, which can be utilized by multiple software, not just ROS. Then we define the joint axis. Joint axis is actually the parts which are moving in the robot that are not fixed. They are moving. For example, in our case, the wheels. What are the axes? Are they going to be rotating in this axis, which is coming out of the page or going inside, or it is going to be rotating along the Z axis, making the wheel go like this and this? Not useful. Okay, so we have to fix all of the problems with the URDF by performing a joint axis test, what I say, in the ROS. Then we go to the plugins. Now, whenever we have a robot, we have to start taking information inside to the microcontroller, obviously, from the robot. That is being done with the sensors, right? In the real world. In simulation, that is done with the help of plugins. In Gazebo specifically, we will be writing some camera. You can see this one is a camera sensor output, which can see in front of itself. Two balls, not this one, square. And the second one, you can see small red dots are because of these LiDAR sensor that as a plugin we added into the robot's URDF. Then we perform a simulation set, which is setting the environment of the robot, how the environment is going to be and how the robot is going to be inside that environment. How means where specifically the robot is going to be. For example, these are some blocks I have placed around the robot, and the robot will be dodging all of these blocks with the help of LiDAR sensor and going away without doing any accident, which is obstacle avoiding. That is what we will be doing. Okay. Then writing algorithms that I said. Obstacle avoiding is an algorithm. We will be writing it in the environment, but the algorithm writing process is at the end when your robot is ready, when your environment is ready, and everything for the robot is set. Okay. In this course, throughout, we will be utilizing Python only. Okay. You can see this is Python, and we are not going to use any other language. I think Python is the easiest one to start with. The two projects we will be doing is first is obstacle avoiding, and the second one is wall follow behavior. I will explain what wall follow behavior is and what is the environment we will be using or building. Object-oriented Python specifically we will be using, and this is a must for any robotics programmer to understand the object-oriented concepts by themselves. Okay, I will not be teaching OOP first. Okay, now. The third project is very interesting, in which we will be utilizing this Prius hybrid model of Gazebo to perform line following. A very common robotics project, line following, but it is going to be done with the help of this camera that we will customly add it. There will be a road on which we have a pattern of line, and this car has to follow with the help of camera, which means this Prius hybrid is going to attain computer vision as we will be programming it to follow the line. It is going to be very interesting how we will dissect the problem and solve it. In the last part of this course, I will be going through different robots, specifically TurtleBot robots. There are multiple versions of it, to make you understand how you can obtain or learn about new things in ROS from these commercial robots and install them into your simulation for your custom robot. Although you can utilize the simulations of these robots freely, but if you want to add some characteristics of TurtleBot into your robots, how you're going to do that. Okay, that will be it for this course, and let's get started with the first topic of creating the package and URD. Now let's start this course by creating first our workspace, and then we will be creating our package. Package is a very interesting thing in ROS. If you have taken the first ROS 2 course, you would have an idea how package is very interesting thing. It contains all of your source code for your robotic simulation that can be put into a workspace. Okay, I will not be detailing it again. Now, the very first thing, according to our practice, we will create our launch folder, then our URDF folder, and then we will tell all of the paths that we are going to be utilizing in the simulation to our package and tell what nodes you need to execute in this package. These things are very important when creating a package. Let's take a look how we are going to do that. Okay, let's get started with the creation of our package. I'm going to open up a terminal, going into my workspace, which is ROS2 workspace, going into the source folder of this workspace, and here I'm going to create the package. Okay, ROS2 package create, name of the package. I am going to say it to be rover for the first package, and build type to be Python, and dependencies are CLY. That's fine, let's create it. It's done. I am then going to make certain directories into the package we have created. As we have discussed, I'm going to first add this package into our workspace, and that is going to be home, ROS2 workspace, source, rover. Let's add it. We have this package in our workspace. I'm going to create certain folders, launch folder, and then the UID folder, and that's it. Our package is ready. Are you sure? No, currently it is not ready. We have to provide the paths to these newly created folders as well. And we can do that by just going into the setup.py of the package. And here I'm going to paste the commands that I'm not going to type. Import OS, and another thing we need is import globe from globe. These are the two libraries we require to provide the paths of our newly created packages, launch and UIDF. In launch file, pick only those files which have .py extension at their ends. Okay. Now we are ready with the linkages, and we are now going to create first URDF file. I'm going to say rover.urdf. I'm using VS Code. If you have not installed it, I have guided the students of the basic ROS 2 course, in which I have detailed about Visual Studio Code installation, and the extension I'm now going to use, which is this ROS by Microsoft. You can utilize it easily. It is very awesome. Rover UIDF, Universal Robot Description Format or file. I don't know. First, you need to understand the tree structure. What is the UIDF telling you about? Although UIDF is all about XML programming, but you have to keep a tree in your mind so you can write the code in the XML for the UIDF. So we will first interpret this, and we will learn more about the UIDF. What it is telling. I will be ignoring these values of distances, so to basically decrease the difficulty of understanding this tree. There is a link. I will be drawing arbitrary shapes. There is a link of triangle shape. Okay, and it has a joint. It has a joint. Let's say at this point, the joint thing is being told by that point, that XYZ value. Then there is a joint number 2. Let's say at this point, there are 2 joints on this link number 1. Link number 1. Let's create the second link. Link number 2 is with the help of joint number 2. Link 2 is going to be, for my easiness, is going to be represented by a square. Link number 3, that is going to be represented by a circle, as I want it to be a circle. Then there is a link number 3 which is connected to link number 4, that is connected to link number 3, and that is going to be what it should be. It should be an oval. I'm going to now draw the joints. First, joint number 1 is this one. I will name it J1. Then there is a J2, and we have a J3 at this point. Links are the bodies that are just simple physical bodies, but they don't tell you about the relation in between the bodies. Okay, so there comes the joints, which tell you about the relation between multiple links, the physical bodies. There is some sort of a relation between the square and the triangle at joint number 1. There is a specific relation between the triangle and the circle. Same goes for the L3 and L4. There is a specific type of relation in between them. Now, These joints are going to be of multiple types: fixed, revolute, continuous, and many more. So I will not be detailing right now. We will be utilizing these three mainly. That's why I have written only these. So all of the links have a specific relation with the other links. Not everyone with everyone. It is not like that. You can see only link 4 is connected to link number 3, and link number 3 is going to be connected with the triangle link number 1, but not with the link number 2. That is an important point to understand. Rover, the robot that we will be creating and making all of the awesome projects out of it. So what are the links and joints? The first link is going to be a square, this black one, a square base. I will be calling it link 1 or base or chases, I don't know. Now, the next one is about creating 4 different wheels on the sides of the robot, and we will be giving different names to it: link front, right, link back, right wheels, like that. We will give a lot of different names, you'll see. Then we have a sensor. At this point it will not be sensor at that one, but first we are going to create a physical body, then we will assign a sensor. This is going to be LiDAR link, and this is going to be camera link. Now all of these links have a specific joint for them, right? All of the wheels are going to have a joint of revolute type, which means all of the wheels are going to be rotating in a certain axis, like the standard wheels. They're not going to be having multiple rotations. That's not what I have built in this robot. Link of the LiDAR, that is this one and this one, LiDAR and camera are going to be fixed links, meaning these are the joints that are not going to move, and we don't want the camera to be moving as the body moves. We want it to be fixed at a certain location. This is a basic understanding of the UIDF for our rover robot. So if we draw a tree for our rover, what it is going to be: first it is going to be a base, that is going to be a fixed. It is going to have a joint number 1, joint number 2, joint number 3, and joint number 4. And you know why we have direct joints like 1, 2, 3, 4? Because these are the joints that are going to be further connected to the new links: wheel number 1, wheel number 2, wheel number 3, and wheel number 4. So these are going to be 4 joints. The next 2 joints we have are joint number 5 connected to the camera. This is another link. Then joint number 6, that is going to be connected to the LiDAR, and that's it. This is going to be the tree of our robot. None of the joint is interconnected with each other. All of them are directly just connected to the base joint. Okay, that is our UIDF in a tree structure. Let's program it, and we'll visualize it with the help of VS Code. Just for your interest, I am going to show you one interesting thing. This is a PR2 robot, and this robot is very popular among the research community. This is the tree of this PR2 robot. Oh my god. Too much information, right? Everything is not clear enough to read for you and make you understand a little bit about it. The main point here is why it is so much complex. Because this robot is containing a lot of things. First, it is containing a base that is sort of a mobile robot that moves on the ground. Okay. The next thing is this robotic arm. And again, another robotic arm. At this point, I think it would be more than 5 degrees of freedom, or almost 6 degrees of freedom. I'm not sure about it. So 6 degrees of freedom on one side, 6 degrees of freedom on the other side. A mobile robot of, let's say, differential type robot, skid steering robot, and then a LiDAR here, a depth camera here, and a joint here. Again, a sort of camera here. So there are a lot of things on the PR2 robot. That's why the tree is something very scary. In our case, it is going to be very simple, and you might have seen the programming is very easy, I know. But what about adding the sensors? Let's talk about it. First, understand the sensors, and then we'll add them. Okay, let me get you to this point where I have created the basic first link. I'm going to call it chases of the robot. This is going to contain the basic black box to which everything is going to be connected. This is going to be fixed link, and it is not going to be attached to anything with the help of joint. Okay, saving it, Control S, Control Shift P to open up this command palette, and I'm going to press ROS Preview UID. This is going to be available to you only if you have installed that ROS Microsoft extension. If you are unable to find it, just like ROS, and there are all of the ROS commands you can execute in which you can find ROS Preview UID. I'm going to run it, and let's visualize it. So this is the basic first link we have created, and its name is chases. It is a box type, and similarly with the visual tag, the things that we type in the visual tag, we have to also copy and paste them into the collision tag. Okay, same properties. In visual, obviously we provide the color as well. We have set gray. I don't know why I've pasted this color value as well. Now I'm saving it, and you can see the changes. I'm going to do Control Z, undo, and now I'm going to save it, and you will see the change in its color. You see, it became gray, and by specifying this color, the value is obviously applied to it. Whenever we save a thing, the changes will be applied to the UID viewer. It is so awesome, saves a lot of time. Now I am going to add another link, and I'll show you there are certain things that were not in this link, but in the next link they will be, because that link is going to be a link with a joint. So let's see. I have added this link named wheel front right, meaning a front right wheel. Inertial properties, these are very important properties utilized by Gazebo, not this UIDF preview or RWIS. These properties are required by the UIDF structure, and specifically Gazebo, because Gazebo is dealing with the physical properties of the model that it is simulating. Now, I have provided a mass value and inertial values. There is a proper workflow of finding the inertial values that I will not be going into. You can find on the Google. It is available on the Wikipedia page. Now we have defined the inertial values for this one, although for your understanding, I have given them very small values to keep away from all of the collision issues. Now, visual properties. In visual, obviously, we are dealing with the visual apparent bodies of this whole description file. We have a cylinder of radius this and length this. I'll save it, and you will see the changes. Currently, I'm not saved it because you can see the white dot on it. So there are collision properties, as we have seen earlier. There is a constant coefficient as well KPKD. These are because of the resistance to this joint, the wheel joint. Okay, although the robot will not be that much good with the drifting because I've not added damping. But if you're just starting ROS 2 as first ROS ecosystem, I don't want to confuse it. That's why I've not added things that are necessary but not essential. Okay, now the here link is completed. Link wheel front right is completed. We are now going to add a joint. The very first time we are going to add a joint. In this joint, you can see we are providing a name and the type of joint. As we have discussed in the UIDF section, there is a tree in which we define the tree with the help of links and joints. Links are connected with the help of joint. This is the point where that theory is applicable. What is this and what is this axis? Now this parent and child is actually a relation in between the links. Parent is the one to which the link is connected. Okay, in our case, chases, this brick is the parent link and the wheel front right wheel is going to be connected to it. So parent is chases and child is wheel front link. So this makes that a tree that we talked about. Similarly, we have the wheel front left wheel and same properties, only the origin and origin is different and the names are different. Everything else is same. I'm going to press Ctrl S and you can see there are two wheels now visible on the robot. Now I'm going to do certain changes to help you understand more about UIDF. If we change the place of our origin of the joint, let's say in x-axis I want it to be 1, Ctrl S, and you can see the left wheel has gone, it was 0.25, so 0.75 ahead in the x, and still it is connected to the robot. In our ways things would work fine, but in gazebo the robot will fall on one side because of the physical issues there. So I'm going to do undo here and save it and it will get back. If I increase the size of the chases, for example, geometry to be 2, it will be a bigger brick then, but because of the origin of this chases is at the middle of this whole body, the wheels did not move. If I move the origin from this chases UIDF or this link, the origin of this link, then the wheels would also have moved. So I'm going to undo it because it doesn't look good. I am then going to change one more thing, and this is axis. If I change axis from z-axis to y-axis, this is x-axis, y-axis, z-axis, so I'm setting 1 for the y-axis. Nothing will happen right now, but we'll see the issue when we will be working on the artworks. Okay, I'm setting left wheel joint to be 1, saving it. No parent changes, but a huge issue will be created. I think you are good with understanding of origin, axis, and creation of the body. If I create the cylinder geometry to be 1 in radius, you'll see the wheel will get way big and I think it is not feasible with the body, so I'll undo it, and that's it. So simulation is understanding things that you are telling it. Okay, no intelligence. I'm now going to add more things into it, and now you can see I have front wheels as well, and blue brick, which is going to be the LiDAR, and then camera link, which is not visible. Now it's visible. It is sort of a sphere, not a sphere, it's again a cylinder, but you can see I just created these parts of the robot and provided names that I will be giving properties when we will be working with gazebo. Same whole process is same, adding the bodies, adding the geometries, adding the links, adding the joints, everything is same. One important thing, if your robot is not visible here, for example, if I create a syntax error here, if I delete this or comment out this, I'm going to save it. There is no issue, but let's cause an issue with the link. It was a joint, so let's save it, and the link having the issue has caused the system of UIDF preview to remove that link. I'm going to correct the syntax error. Similarly, if I produce any syntax error inside of the UIDF, things are going to get worse. And this is very good preview. It is providing previews with simultaneously with the errors in the UIDF. That's awesome. Always is not that good. Always is not going to show your robot anything of your robot if there is an error in the UIDF. Okay, so let's write a launch file for your robot. The next thing we have to do is to create launch files to launch our robot in the simulations. We don't have to provide the paths. We just need to run the launch file and it will do this good stuff as we have discovered in the ROS course. I'm going to say it again because I'm not going into detail, the detail I have gone into in that course. Okay, so creating a new launch file, I'm going to call it one_arvis.launch.py. Why the name is .launch.py extension? Because ROS2 says it. Okay, previously launch files were XML syntax or XML language was used, but now launch files are programmed in Python syntax, so more power to us. The basic structure is going to be simple, like this, in which there are certain import files that I will not be explaining right now because we are going to use it afterwards, but this is the basic structure in which we just need this launch description thing. We don't need that package share directory and node right now because we are not importing anything. It's simple launch file plain, but there are multiple ways to write the launch file. We are going to be writing in the very simple format. Okay, now when you want to visualize your robot UIDF in the ROS system, the robot which have a model with the help of a UIDF or any other mesh created files, you have to publish transforms for your robot. The very basic concept of ROS, it requires states for the transforms to make the robot move. The first thing is transform for the fixed joints and transform for the moving joints, non-fixed joints. So we have to first add them and then we can visualize our robot. Now here we are with a lot of things pasted that were not previously in the launch file. First, what we need to do is tell the system what package we are utilizing. Then we tell the system what UIDF file or any other file that we want to load into your system parameter server in ROS case. Then what we do is call the nodes and provide that robot to these state publishers. That's the whole system of publishing your robot into the ROS system. Now the package directory is the rover. So this tells the system what package do you want to use and what file in that package do you want to utilize. In our case, rover package and this rover.uidf. The syntax should not be wrong. It's a Python file. Indentation should be taken care of, and the UIDF file is just created through OS path join stuff. Simple Python stuff. Coming to the nodes, the ROS stuff here is package name is robot state publisher. If we open up a terminal, we can check things from here. If we have these packages or not. ROS2 run robot state publisher, and the executable file I'm looking at is I'm pressing double tap, so it tells me all of the executable files in that package specifically available. So robot state publisher is there. So I have this package installed. Talking about the next package, ROS2 run joint state publisher, pressing double tap. There are two packages, simple joint state publisher and GUI joint state publisher. The executable in GUI package is there, which I am calling here. Okay. If these are not present in your system, just do this simple thing. ROS2 sudo apt get install ROS2 ROS Foxy joint state publisher, or press tab and you'll get the packages, press enter and they will install. That's how simple it is. Now coming to the point of nodes. I'm going to add another node because states are published, but I want to visualize it in a simulator. The RViz is going to be the simulator I am going to be working with. So pasting the commands that I've already copied, I'm going to delete one thing. I'll talk about that later, and that is how it is going to be. RViz package executable RViz, and I can provide any name I want, but I'll go with the convention RViz too. Just so saving it. The next thing we need to do is to go into our workspace and perform call build on a selected package that I want to build on. I don't want my whole workspace to be built, okay? So rover has been built, but building means my launch files have been copied into the shared directory. If I call them here, ROS tool launch rover, I'm pressing tab and it is completing, okay? So it says with RO double tab, there are a lot of possibilities. So I'm going to now type the whole name, ROS tool launch rover, and the name of the launch file was 1_RViz, right? There are other options as well. There is a small one and a big one. Why? Okay, I have two packages with the same name, rover. So with the small rviz.launch.py, okay? So I'm going with this convention, pressing enter, and let's see. Okay, there are a lot of things that might not pop up on your screen because I have certain settings saved in my system. So for example, this laser scan, I'm going to remove it right now, and this image as well, the TF as well. This is our robot, which should be visible to you when you were developing it in the URDF preview. New thing is joint state publisher. The joint state publisher is going to publish the transform for the joints, and robot state publisher is going to take the joint state and publish the parameter server, and a lot of theory you can find on the Wikipedia. If you don't publish the joint state separately, things are going to cause issues. I am now going to check the joint access that I have discussed in the theory portion. I am going to add the transform that are required to test the joint access. I'm going to bring in this joint state publisher GUI, which basically publishes the joint states of my robot. If we play with this one, you can see my wheel, which is front right joint wheel. Although it is not front, I don't know why I did this mistake in the naming convention. It doesn't matter to ROS, by the way, but still there is an issue. Front right joint wheel is an issue. So if I change the values for the joint states in RViz are updated, and you can see the robot's wheel are rotating. If you do with the second one, there is an issue, and that issue is the value of the axis we changed. I'll show you in the URDF. So other wheels are working perfectly fine, right? Yes, they are all fine, all are rotating along the Z axis. But this one, front left wheel joint is rotating on the wrong direction. We don't want it to be rotating in this joint axis. This is a thing that we want to fix first, and then we'll move. I'll press save and it will save, because next time when I run, this same configuration will be open. If I open up this rover.urdf, in which I was dealing with wheel left joint, in which I changed the axis from Z axis to Y axis, I'm going to set Y axis to be 0 and Z axis back to 1. That's why I caused an error, so you can learn more. Call can build, again pressing upper arrow keys to bring in the commands that we have written earlier, pressing enter, it has compiled it. Let's run this rviz.launch.py again. Where is the GUI? Here it is. Let's check it. Now wheel front left joint is working perfectly fine as we desired. So our robot is ready. We don't have these joint state publisher for the joints which are fixed. Only non-fixed joints have these bars which publish the joints. This is a very simple and useful tool to test your URDF joints access. Okay, so our robot is ready, right? Let's now bring this robot into Gazebo, in which physical properties of the robot can be seen. Okay, so closing these things. I will be creating a copy of this launch file, and I'm going to rename it because the basic syntax is going to be the same. Let me gazebo.launch.py. Okay. So now in this gazebo.launch.py file, I will be needing the package and the URDF from that package, because this package directly, this line can be deleted if I copy and paste everything in this. But to keep the code clean, I have created a variable, provided the OS path join that variable address of the package, and then URDF is obtained from there. And that URDF is then utilized by robot state publisher, GUI joint state publisher. I'm now going to add gazebo commands that I want. But you can see there is an issue of execute process. It is not found because I have to import one another thing. I can write the commands in front of you, but I don't think that could help you a little bit. You need to understand the theory and the implementation. Rest, you need to do the practice on your robots, your custom commands, so you can learn. But if I start typing in front of you, things will not make sense to me. Okay, execute command. This one, if we comment it out for a moment and just run this node in which gazebo ROS is executed, and gazebo ROS is the package, executable spawn entity.py. Name is going to be URDF spawner. This is the name of this package, not the result. And output is on the screen. Topic is going to be robot state publisher robot. This topic is the general topic to contain the robot description in ROS system. Okay, multiple packages are using robot descriptions from this specific topic, which is going to be published by spawn entity executable of gazebo ROS package. Okay, things are going to get a little bit confusing from now on because I am throwing new things at you, right? But you have to stay calm and focus, and you'll learn. But this is spawn entity. Where it will be spawning, we need to run the execute process of gazebo. We want the gazebo to be running, right? So we can just run gazebo as well in this command. This is basically simple command. If I type here gazebo, it will execute and gazebo will open. This is what is happening in this command. If I type the same things right there, gazebo, then verbose, and then this thing .so, and let's take a look. It runs. Yes, it runs. There is an error, but gazebo runs. Everything is fine. I was facing certain issues, that's why I added that verbose lib gazebo ROS factory, but I don't think so that would be necessary, and you can replace this execute process as the ROS is further developed and easy calling processes are developed. Okay, so this execute process is just running gazebo. That's it. Then the next node is running the spawning of the robot into your gazebo environment. Okay, let's now run the Colcan build first, because we have made changes in our launch.py file, and we have created a new launch.py file and changes in the launch file, but there is an issue. We have to get into our workspace first and then run the Colcan build where this package is. Now changes have been applied. I am going to run ROS2 launch. The package was rover, and the launch file is gazebo, gazebo.launch.py, and things are running. Arvis should also open and gazebo should also open. And here is our robot in the gazebo environment as well as in the Arvis environment. In gazebo, if I move the joint state gazebo, robot is not going to move, because if I change the joint states of my robot, robot is going to move in gazebo if I write if actually the wheels are rotated, not the joint states. Okay, so this is the difference between gazebo and Arvis. Let's now close Arvis. We don't need that. I am going to do certain things. We don't need the GUI state publisher. There are some errors. These are the other models that I used as Blender signboard. You don't have to worry. I think you will not be getting these errors because I created certain directories and I deleted, but they got added into gazebo. Now spawn entity UID of calling. Why it is red, I don't know, but this should not be red. Spawn status successfully should be written in green. Arvis is load, okay, process is finished greenly, but I don't know why the text is red, showing as it is an error. I've closed these two things, and a robot is in the gazebo environment. It is a little bit drifting, right? If I zoom it, you can see the robot is continuously drifting to left side. These are certain problems that you have to fix with the coefficients or damping of your joints. So these values, the values of inertia also matters in this. So all physical properties matters when we are dealing with gazebo and such things. But for now, I will not be changing those values, and we'll go with this same problematic robot to make you understand the basic workflow. I don't want to confuse you with the physical property tuning right now. Okay, what we can do with the gazebo is view a lot of physical things. Inertia, and I think I've set the values of inertia to be very, very low. And then collision, everything is going to be in collision, and then the joints, what has the joint axis, and a lot of things, skeleton and stuff like that. So you can play with this gazebo a lot, and that's it for gazebo and Arvis simulation of the custom robot that we just created. Let's get to the plugin installation part. First, we need to understand that. Our robot is completed, and we can visualize it in Arvis, a very good software. We can also visualize it in gazebo as well. The thing is, let's make that robot useful with the help of plugins and sensors. The word gazebo is mentioned with the plugins because gazebo provides those simulation plugins that can be interfaced with the ROS. Arvis does not provide plugins that can be interfaced with the simulation environment. They just visualize the sensors output. So Arvis is basically getting information about the robot, what robot is seeing, and gazebo is about getting information about the environment, not the robot. So 3 plugins we will be installing, and they are very interesting plugins: driving plugins, LiDAR plugins, camera. Driving is going to make the robot move forward, reverse, left, right, and stuff like that. Important point here is LiDAR, which is going to be the main reason for all of the projects we have. LiDAR is going to have a spread like this, and anything that comes into this vicinity is going to be detected as an object. If you place a circle here with a different color circle or ball here, it is going to say that I have something from the robot is here, something in between this distance in my vicinity, and LiDAR is going to tell us about that, not the circle, the distance and the location. We can identify it. The second thing is camera. Camera is very important. We are just going to install it. We will not be writing an algorithm to utilize this camera, but we will install it so you can learn how camera can be installed and how to process it, how to visualize the output of the camera from the simulation. It is awesome. Okay, for every link that we create, for every plugin that we will be installing in our robot in the URDF, because URDF is going to tell us about the robot, and plugins are also going to be installed in the URDF. They all are going to be requiring a type, which is actually a plugin name: lib gazebo camera, lib gazebo control, lib gazebo lidar, stuff like that. Link attach. All of the plugins require a link to be attached to or defined inside of that link, which means in a robot we define the whole structure with the help of names of the links. So plugins require a link to be attached to. In our case, we have defined a specific link, LiDAR link and camera link, which will be connected directly to these plugins. Driver plugin is a little bit different. It is requiring about the wheels of the robot, and it is going to produce a topic. What is a topic? I will explain it. Properties. Properties are basically the name itself, the properties of this plugin. In our case, specifically in regards to LiDAR, we can have a full span of lasers throwing out of a robot in a circular pattern, but we are going to just half it and utilize only 180-degree span of these lasers because it's my choice. You can make it 360, increase the number of LiDAR rays, and a lot of stuff in these properties. That's awesome. And with respect to camera, you can set the properties of image and image height, its pixel, and in my case, I think I have set 640 into 480 for the image size I want from the environment. You can increase the field of view, and a lot of stuff with the help of properties you can change, and you should change. Now coming to the point of topics. Every plugin is going to output a topic to make it useful, and you know why. Topics are very important, so we can publish the data, and we can subscribe the data and do a lot of stuff, and then again publish it. That's how it is going to be. Camera is going to publish images frame on a specific topic, image raw, I guess. The very popular CMD well is going to be the topic published by the driving plugin. The next, LiDAR is going to publish scan topic, which we will utilize and see how cool is it. Okay, let's install these stuff. So here we are with our robot rover, which has 4 wheels, 1 base, camera link in the joint. Let's take a look on the camera and joint link first. This is the camera link, okay? And the geometry is a simple box. This blue one is the camera, okay? I was thinking it is a LiDAR. Now LiDAR is a cylinder that is in front of this black brick of chassis. What we are going to do is add differential drive controller to this robot. And it is going to be very simple. Just I'm going to uncomment this, remove the comment from here, and I'm going to add this robot tag at the end of this plugin. This plugin is not going to appear in URDF preview. Obviously, it will be visible only in Gazebo, not visible. Topic will be available to be interacted. What this plugin contains, it is a Gazebo plugin, and that's why there is a Gazebo tag. We have the name, whatever we want to give it. The important thing here is the file name that I talked about earlier, lib gazebo ROS differential drive.so. This plugin is a little bit different because it is not going to be fixed to a link. It is a plugin that is driving the robot, and there will be multiple controllers inside it which will be controlling the robot's motion, actual motion in gazebo, meaning actual motion in real world. Let's say if we write the hardware interfaces, this plugin is requiring wheel front left joint, wheel front right. One interesting thing here is we are just driving this robot with 2 wheels. Only 2 wheels are actuated. Same plugin is utilized in Dolly, which only had 2 wheels. The other two wheels, then the other 2 wheels of the back, left and back right of robots are not actuated. This is the point where I want to let you do the task of adding the back, left, and front wheels controlling in the same plugin. There are certain parameters that you can add into this and make it completely 4-wheel actuated controller plugin. And I've done in some robots for your help in ROS Ultimate Repository, Learning Repository. But for now, I'm just going to control 2 wheels, front, left, and front. That is going to be enough to control the robot. Wheel separation, you have to provide the distance between the 2 wheels. Wheel diameter, we can calculate this diameter and wheel separation by simply, where are the wheels? Let's check if we preview it. Wheel front, right. Okay. If the distance is 0.4, is that the distance between, if I set it to 0, I'll find it. Okay, it is from the base. So it is from the midpoint. It is 0.5 on this side, right side, and the other one is on the 0.5 on the left side. That's why the wheel separation is 0.8. Wheel diameter is 0.3, as radius is 0.15, so diameter is said to be 0.3. These are the parameters that are required for your own robot. If you change some things in the links, bodies, or what should I say, meshes, these values will not work. Okay, so you have to put these values very carefully according to your robot, as this plugin is going to calculate your kinematics of the robot, and if you have not provided correct values, obviously mathematics is going to produce wrong results. Maximum wheel torque, acceleration, ohm to ohm transform, publish wheel transform, and what is the odometry frame you want to produce, base for robot's base frame chases the base frame, and you want odometry frame. So this is the plugin that with these small values and these small property values, we are going to be having a very useful result. Let's first build it. Let's go into this workspace and perform Colton build. Colton will packages select robot. And now ROS2. One more thing I'll be doing, I will not be running RWiz again and again here. I don't need it. So I'll comment it out and again call can build it because I made changes in this launch file, and I guess this is the launch file. Yes, this is the launch file. We are now going to dissect a lot of things. Okay, I don't want the state publisher GUI version as well. We'll go with the basic one, and we don't need to test access again and again. So what is the problem? Robot model was not robot invalid XML junk document. Okay, there is an error in robot.urdf. Okay, there is an error in URDF. I have to comment because there is another code down there, but I will be exploring that when I will be explaining. So that was the error. Now close gazebo, and it is great. You also experience that if you have an error, your robot will not be appearing in gazebo or RWiz. Okay, so no more GUI, no more RWiz. We are just going to have the robot in gazebo. This time I think everything went very well. These are the warnings because of the parts that are deleted. This is our robot, and is it? Yes, it is drifting. Okay, it doesn't matter right now. So what we are going to do is to go in detail of the topics that are available. ROS2 topic list, the available topics. Tell me about that. And we have a robot description in which this robot is available. And this is the important point. If you have taken the ROS2 basic course, you might be very experienced with this topic because you have played a lot with this topic specifically. For you only, I am going to ROS2 topic info CMD well. Getting more information about it. We don't have a publisher, we have a subscriber of this message type. What I'm going to do is run a node ROS2 run teleop keyboard. I want the keyboard tele operation, and when I run this, it is going to ROS2 topic list. If I list it, it is going to be ROS2 topic info command velocity. It is going to tell me that there is now a new publisher which I have just ran this topic. If you don't have this package, you can install it. If you're not understanding what I'm doing, I've detailed this process of what I'm doing right now in the force. Okay, I want you to take a look. This is now going to make the robot drive. I'm going to press these keys, moving around keys, because it is a non-holonomic robot, so I'm not going to be using these. I'm going to be using simple I to move forward, L to take the right turn, and this would be more apparent if I enable the inertia and joints. It would be more visible to you. If I make it a skeleton, yes. Now it is more visible what is actually happening. Okay, now I'm going to stop it. Only this one and this tire is only actuated. These front wheels are not actuated, and I want you to actuate them. Currently they are moving because of the inertia, but now when I turn it, only the wheels on the back are producing the motion. You can see they are not moving as these two are moving in opposite direction. If I turn it in the other direction, their rotating direction will change. Very interesting thing about this robot regarding the driving of the robot and the controllers, this libgazebo ROS control.so file. Now it's time to add another plugin, camera and LiDAR plugin. We'll install both of them simultaneously. I'll close this one, but before closing this, I have to close this one, and let's close this one. I have these written already. I'm just going to comment the comment, and I'm going to bring this robot back here, which means robot URDF ends here right now. I have to remove errors if there are any. Now let's first discuss this camera plugin. In the camera plugin, we say a gazebo reference of camera, sensor type is camera, type is camera, name is camera one. If you want to give any value, we can give it. You can say Lukman camera, and update rate, meaning 30 messages are going to be sent per second. 30 images are going to be sent from this camera. So do you understand the magnitude? I'll do the bandwidth and frequency test as well. These are simple properties that you can simply understand by looking at them, and I obtained these values from the wiki page of this gazebo plugin. 800 by 800 is going to be the image in RGB, and then the controller plugin. Now this one is interesting. I want it to be true, so in gazebo it tells me what the robot is actually seeing, what the camera of the robot is actually seeing, and update rate here is, I don't know why it is set to 0. We have already set it. Camera name is going to be this, and the topic it will be publishing on is going to be namespace camera and image raw. Image raw is the main topic on which images are going to be available in ROS ecosystem. We can get that. We don't want camera info, but let's publish it. Frame name on which this camera is going to be attached is camera link. Let's search it if it is there or not. We have only one camera link. I think this was the name of the link that we had. Camera. What is the name of the camera link? it is camera, simple camera. Yes, I was right. So to the link camera, it is going to be attached. Now, LiDAR plugin is exactly same as we did with the camera. Names, visualize true, update rate. But one thing, the output of the LiDAR is going to be remapped. Whatever its name is going to be, its output is going to be scan. Okay. This means whatever the output of the LiDAR scanner is going to be remapped to scan. This is not going to affect right now, but in future when you will be working with different stacks in ROS, navigation stack, they require scan topic laser values, okay? Only. You can remap there as well, but I want to just show you that you can do it in the plugin as well. Now output values are going to be of this type. Frame name is going to be LiDAR, samples 360, meaning 360 values are going to be provided, not the span. And this is the angle from 0 degree to 180 degree of span. You can change it to be 0 to 2 pi, 6.24, and the whole circle will be completed. I'll show you and some other properties. This one thing is very interesting. I'll add it more. Gazebo reference and gazebo material. Oops, gazebo material. Let's make it. Whoa. Okay, that's it. This reference is actually giving colors to the robot's body. In gazebo, you have seen that the color of our robot was totally white, and we don't like it. So I'll add colors to my robot. To the sensors, camera, and LiDAR, colors are provided, but for the chases, for the wheels, colors are not provided, so I'm going to provide some awesome colors. First, we need to have the names of their links. LiDAR and chases. What is the name? What is the naming convention of the wheels? Okay, I got it. I'm going to paste here again and again. 4 wheels and 1 chases. Left wheel, back right. Wheel, front right. Wheel, front left. And that is a great help when you have a naming convention followed in your whole robot. I will be setting all the wheels to be red, just because I like red, and the chassis is going to be orange. Too much strong colors applied to the robot. Let's check if the syntax is right or not. These colors are only going to be provided in gazebo. They are not going to be applied in RViz. In RViz, the simple geometry color or visual color applied is going to be the main color. Oh, I have to go into ROS to workspace and then call and build it. Now you can see we have the robot colors applied perfectly. The LiDAR values are very interesting. 0 to 180 and 360. These rays are actually 360 rays on 180 degree span of laser. There is a camera as well. I don't know why the camera is not visually appearing. I am going to first check if the camera is publishing or not. Let's do ROS topic list. And these camera image raw is publishing, but let's take a look. ROS2, RQT, GUI, RQT. This is a package that is very awesome for debugging purposes. I'm solving a little bit of problems here, and I don't know why it is not. ROS2 run. There are some small things that you always forget for no reason. Now I'm going to set it to be camera 1 image raw, and you can see I have something visual. As this camera is publishing things, I am going to see, yes, you can see the camera is working perfectly, although it is showing this as well in the field. We don't want it, we can remove it, we'll see later. But main thing is, camera is working, LiDAR is working. How do I know that LiDAR is working? I'll show you in the next project how I know that LiDAR is also working. So that's it, our camera is working, and LiDAR plugin is working, and also our drive control plugin is also working, right? So that's how it all works. You have successfully interfaced your robot with all of the plugins that we design. Isn't that awesome? Now I think let's start utilizing these plugins and make a very awesome obstacle avoiding robot. To do an awesome project, obstacle avoiding, with the help of LiDAR sensor installed in the UIDF with the help of Gazebo plugin. So how we are going to do that? First, we have to understand certain things. How Gazebo plugin about the LiDAR is providing us the data. It's not the same as other sensors. You can see the picture here I have. First, this span is going to be visible to us in front of the robot, meaning anything that comes inside of this span is going to be detected by the robot, and we can tell the distance to that object, any object, okay? First, we have to do is to find in which area or what is the direction of any object placed in this span of lasers, okay? That is first step. So what we will do, we will perform this first task of area division, okay? Let me skip it. This is how I'm going to perform the area skipping, which is total number of rays. We have 360. Okay, we have defined in the properties of our LiDAR. So we have done 3 area divisions of total 360 rays along 180 degree axis. Okay, now area number 1 is going to be from 0 to 120. Area number 2 is going to be 120 to 240, and area number 3 is obviously going to be from 240 to 360. So ray of the laser from the LiDAR is actually a value in an array. Okay, I know it is confusing. So what I have done in this division is, first, this one is the area number 1, this one is the area number 2, and this one is the area number 3. Whenever we have an object in this area, we can check that area 1 has detected something, and we can tell it is this 120 degree area span in which an object is placed. It is not in area number 2, not in area number 3. We can find the object inside an area with the help of this division. How do we know that there is an object? All of the values of the laser scanner is going to be having a value of infinity. This is an important point, infinity. Whenever an object is placed inside the span of the rays of LiDAR, what will happen? Of those specific rays coming out of the LiDAR, those rays value will be changed to a certain value. For example, these three are going to have 2.4 and 3. These are going to have these three values of these dotted three rays. All other will have a value of infinity. So it is again a problem. Infinity cannot be processed. So we have to solve it. Okay, that is going to be done in this data pre-processing thing. Okay, what we will do is first from area number 1, if we have something, because if there is not something, it is going to be giving us a value of infinity, right? If there is something, or you find something by comparing, you get a value of 100. What I am doing here in this equation is the value of area number 1 is always going to be infinite whenever there is nothing inside the span of this area number 1. Okay, whenever there is nothing inside it, the value is going to be infinite. So if we apply this condition, what is minimum of these two, infinite or 100? It is going to be, answer is going to be 100. Okay, that is going to be applied to the same for both of these remaining two areas, area number 2, area number 3. We have to somehow remove this infinity thing and turn it into a number. That's how we are going to do that with simple this logic. Minimum, find a minimum, infinity or 100. 100 is minimum. But that condition does not apply in certain cases. Now this was a holistic solution. What I'm now going to do is the actual solution that has been implemented. So first we have to find the minimum of all of these values. Let's say this is area number 1. We have to first find the minimum of these. So what is going to be a minimum of all of the values from the area number 1, find the minimum from all of these values, and then find the minimum. Now this is one full step because it is a big array. Then I will say, let's say it is minimum of A, I'm going to say. Then I'm going to find minimum from the minimum of A and 100. The same thing that I wrote earlier, but the concept is different now. This is representing minimum from a big array of 120 values. Okay, 0, 2, 1, 3, infinity, infinity, infinity. So it is going to be returning us 0 at this point, and 0 is less than 100, so minimum is going to be 100. What is happening here? In this whole area of area number 1, anything object placed like at this point, let's say, the value here is going to be, let's say 2 for this simple array. We are going to pick this value and say that in area number 1, we have an object with a distance of 2. We are going to disregard all of the rays that are not impacting on the object because they are giving value of infinity. So you have to write this down, solve it, and this will then this will start to make sense. Okay, let's take a look on the output of our LiDAR sensor in action, and serious stuff, right? Now let's first create a node on which everything is going to be implemented. Name of that node is going to be obstacle avoiding dot py, is it's going to be a Python file. I'm going to place the contents here, and that's it. This is going to be the node. It is not going to publish everything. I'm not completed it right now. I have just broken it down. First, whenever we'll run this node, what will happen? This thing is going to be run. Then this is calling main function. In main function, we'll check if there are arguments or not. Create the object of this class. The main thing in this whole node is this class. Then perform the RCL spin of this class object and then shut down. Keep running this class, and whenever any interrupt is called or you send an argument, shut it down. Now coming to the main point, what this class is doing right now, it is not completed yet. We have just discussed the area division only. I'll implement it first and then we'll move to the obstacle avoiding thing. Now obstacle avoiding bot, the class, first we defined a function, a constructor, let's say, and it has a name for the node. When you will run it, this node is going to appear. We have created a subscriber. I'm not going into explaining everything about the syntax because you can find it in the ROS wiki. It is very explained there. It is very much detailedly explained there. I don't have to explain the subscriber and stuff here. Okay, I'm just going to be dealing with the complex algorithm that we will be building to solve the problem. Now subscription creates subscription, and what is going to be the data type? Laser scanner is going to be the data type of the laser, and scan is going to be the topic. The callback function is going to be get scan values. 40 is the buffer value. 40 by messages can be accommodated at a time. I think this is the meaning. Yes. Now linear velocity is a constant velocity that I have set it, and every time when I want to move the robot in a linear velocity, I will not be giving values. I will just call this variable, and it contains the main value of velocity we want to set to the robot in this whole node file. Okay, regions are the actual thing that we talked about. Region 1 to 3, right, left, mid, and velocity self means self velocity, and self subscription and all of the other self stuff is because of the one reason that we want to call them again and again in different functions of this class. Okay, so that's why we are defining certain things as global variables. Okay, now as part of the constructor, so we can call them with the help of self. Okay, in get scan values, the callback function of this subscriber, meaning whenever we obtain any value from the laser scanner, we are going to be falling into this function. We'll process it, and again whenever we obtain a value from the laser scanner, and that is going to be happening 12 messages per second. Now in this function of subscription, we are going to first define the regions and going to print left, right, mid. This is a practice to break down the whole code and understand what actually is happening. Don't go directly to the solution. Okay, in right, mid, left, we are going to be dividing the whole area into 3 parts, and each of these 3 parts is going to have 120 values. If you don't understand it now, I will visually show you and it will make more sense. First, we have to add this into our package that this is an executable. Okay, and I am going to say follow wall, the name of the executable file. The next thing I'm going to do is, let's close it, and what I'm going to do is to provide the name of this file, obstacle avoiding, the name of the package here, that is rover. That's it. We have defined our executable file to our package. Now let's perform the call can build. Call can build. Stop the previous thing. Call can build. We are now going to check if our file is executable or it is not, and is it available to run or not. ROS to run, name of the package rover, and pressing double tap, we have follow wall right here, the name we provided to make the executable and name it to be follow wall. Okay, pressing enter, it will be doing nothing because we have not provided the laser topic. For that we have to run the simulation. ROS to launch rover, and going to launch the gazebo stuff. Okay, This will bring the robot in a simulation and the laser scan values with the camera, but we are not utilizing the camera right now. If we take a look here, okay, 100, 100, 100, what does this mean? We have discussed this. This is actually the value of left, mid, and right. Now, whenever we obtain a value and there is no object inside of this scan, this blue area, value of this portion, only this portion, is going to be infinity. If in a specific area of right, if the value is something, let's say all of the other are infinity and only one has a value of 2.5, the value of 2.5 will be here. And if 2.5 is here, the next one it is compared is 100. So what is less, 2.1 or 100? 2.1. 2.1 is let's take a look how actually does it works or not. So I'm going to bring it side by side and let's bring it here. I'm arranging. I'm going to place an object in the left side. You can see because of placing the object on the left side, or I should say left region, the value starts to change. From 100 it became 2.5. I knew it was exactly 2.5. I will place another object in the same region. The distance has changed to 1.1 because it is going to tell us the minimum distance in that area. Okay, it is not going to tell us about all of the objects in the area. Okay, I'm now going to put an object on the right region. The values on this portion are going to change. You can see 2.7. I'm going to now place an object in the front region. All of the three values are now provided with exactly the distance, 2.11. Interesting thing here is you can have an idea in which direction the object is placed in. Okay, dividing in areas helps us with this thing. If we divide the areas even further, 360 values divided into 360 areas, we can get accurate position of the object with the help of simple algorithm. But right now, it is still very convenient to work with the obstacles in the area because we have defined areas and we know where the area is left area, and we even know the distance from the object as well. So that's awesome. Now there is one thing that will cause a problem with the logics that I have created. There are certain points where the object is going to intercept two areas at the same time, like this one. It is intercepting area number left 1 or 2 and mid area as well. Both are intercepted by the same object. This is going to break the code that I have written, but still the robot is going to avoid obstacles, I think. So let's first understand the logic theoretically and then we will implement it. Which will cause the robot to take action wisely according to the logic we have defined. So the first case is straight movement. Whenever there is nothing in front of the robot or in the left or in the right of the robot, make the robot move in a straight line. Okay, straight direction, straight line, whatever you want to say. So if area number 1, area number 2 and area number 3 value, all of these areas having a value equal to 100. Remember, 100. Actually it is infinity and we have minimized it to 100 because there is nothing. So if it is 100, case number 1 is going to be called. Okay, the next time if we have an object on the right side at this point, okay, area number 1, 2 and 3 is going to be having different values. Area 1 is going to have a value of, if the distance here from the point is minimum from all of the rays impacting on the object, the minimum value is 1.5. Area 1 is going to have a value of 1.5. Area 2 is going to have 100. Area 3 is going to have 100. What action do you want the robot to take is left turn, okay, and that is case number 2. So case number 3 in which we have to take the right turn. Let's remove things, and case number 3, area 1 is going to have a value of 100, area 2 is going to have a value of 100, and area 3 is going to have an object at this point, let's say, and the distance of the minimum value is going to be, let's say, 2.5. And there are other values, not all of them are infinite, because there are multiple rays falling on the object. There are multiple values, 3.5, 4 or stuff like that. I think 4 is maximum. So that is going to be 2.5. You are going to say, now take a turn to the right, case number 3. Okay, final case number 4, in which we have stop and turn full. This is a little bit confusing. There is an object in front of the robot that is lying in all of the areas. Okay, it is touching all of the areas. Here area number 3 is touching, area number 1 is in, area number 2 is touching the most. The object is in front of the robot, sort of a wall. So area number 1, area number 2, area number 3, all of these are going to have a value not equal to 100, which means the object is inside the vicinity of all of the areas, and we are going to say this is case number 4. And take a strong or left side, whatever you want to say. So these are the basic 4 cases that we are going to be programming, and that is going to be our algorithm after data processing, which is going to make the robot obstacle avoiding. Let's take a look. Now we have to implement the stuff that we discovered practically. If we take a look here, we have added a publisher as well. Previously, we just had a subscriber of the laser topic. Now we are going to publish the command velocities of the sensor message, geometric message twist, which is going to contain linear and angular velocities. And we are going to be publishing it periodically. This topic, or this function, is going to be the callback function in which everything is going to happen. And this is the new thing that I just added. It is going to send command velocities. The first thing is I have provided a lot of comments so you can understand easily. Linear velocity is constant. Okay, linear velocity is not changing. Only the angular velocity is changing. So we have to deal with that only. I have explained to you certain cases. Let's take a look on those cases. The first condition is in which there is nothing in front of the robot, then no rotation is applied to the robot. Okay, so this is the case where the values are 100, 100, 100. The robot is going to move in a straight line. Then come the next case in which we have a condition object is on the right, meaning this right region has a value less than 4. Okay, so less than 4 is actually to be the threshold of the maximum distance to an object of the span of the rays. Object is on the right, we have to take a left. If object is on the right region is less than 4, both of the other regions are greater than 4, or in actual terms 100. So take anti-clockwise rotation. Positive values in the angular rotation are anti-clockwise, taking left turn. Similarly, if there is something inside of the left region and not in the right and mid region, take a right turn. Finally, if the object is very close to the front, take a sharp turn. Okay, and I think we should add one more thing here. Add a negative velocity. This will make the robot go in the backward direction and take a turn. So it would be more reasonable. And let's take a look on this code. First, we have to add this code into our setup.py file. Did a mistake. I named it wrong. Follow wall is going to be the next project. It is going to be obstacle avoiding. Why I made this mistake? I don't know why. I have to perform the call and build again. Follow wall is the next project. I don't know why I named it. And obstacle avoiding. Okay, our robot is moving forward as nothing is in front of the robot. If we place something on this side, robot takes a turn on the left side, and if you place something on this region, it is going to take a turn. So that's how it is. Let's bring the robot back here so we can process. Let's take a look what happens. It is, I think, going to cause issues if we bring this thing in the middle. There is no such condition for the middle, but if it gets very close, it should take a reverse action. Yes, it took reverse action and a turn, very sharp turn. Now, when it is avoided the obstacle and removed from all of the areas, it started to move again. It is going to happen in the right, and so it took the left turn. Now that is awesome. Let's bring the robot back again and pause the simulation for a moment and rearrange certain things. I'm going to bring the robot back, make the camera look from his, and I'm going to place a wall of these cubes. So let's see what happens. This one here, again. Let's see what happens. Play the simulation. It is okay. Now things are back. Let's take a look what will happen. When the object is not in the left and right region, robot does not stops. Okay, in the mid area there is no condition applied. Okay, this is the point where you can add certain conditions as it is going to hit. The condition the robot is following right now is unless all of the areas are clear after going reverse, robot is not going to stop. When all of the areas get clean after going reverse because of an object covering all of the areas in front of it, then it will move. So this is sort of a problem. You can solve this by adding some 2 to 3 more cases, and it would be very fun. So that was awesome. Our robot is actually avoiding the obstacles. Previous project would be very easy as compared to this one, as we are going to be diving into deep detail of laser data processing and following a wall. A proper behavior will be programmed into robot, and we'll do fun stuff with the rover, and also including the dolly that we created in the free roster package. Okay, wall following behavior. First, we need to understand the different scenarios we have in this project. This is a robot spreading rays of light actually, and we are going to have wall on this side. Okay, it would not be, let's say it is intercepting the wall. Okay, you know the concept. We have to process the data, find the actual values in different areas as we did in the previous project of obstacle avoidance. In this project, processing is going to be totally same. We are going to reduce the amount of rays in an area. Okay, what I'm saying is the first area is going to be this much small. Let's say, and actually it would be more smaller than this. The second area will be from this point to this point, and the third area is going to be from this point to this point. And that's it. These are going to be the areas we are going to utilize in this wall following behavior, and very good wall following behavior will be implemented with these 3 areas. Obviously, if we add more scenarios, more areas and more conditions, it would be more robust, but with these 3 areas, that's enough. Wall following behavior will be implemented. Now, so what are the actual scenarios we have? This blue square are the walls. First, we want to make the robot move in a straight line. That's an obvious scenario we want. Then we want a specific distance. We haven't done this in the previous project. Yes, we want a specific distance from the robot to the wall, from this point to this point. And how we are going to do that is an interesting thing. We are going to create a proportional controller in which we will be calculating the error, and that is going to make the robot at a specific distance from the wall. Okay. Then we want the robot to turn when the wall turns. For example, the robot is at this point, this specific point, and when the wall turns, the robot should also turn. Okay, like this. Then we want proportional controller as I have described. That's fine. We have to keep these scenarios in mind when we are developing the algorithm. I have further divided the requirements into different cases. Case number 1, laser on the wall. What this case is telling you, we have to keep the laser on the wall to move in a straight line and to keep a specific distance from the wall. These main 2 conditions are going to be fulfilled in this case. So let's say we have this span from the robot, and our robot is like this here with some wheels, and we have 3 areas as we have described earlier. This one, and this one, and we are going to neglect all of the other lasers. We are going to even not process all those. Now, this area number one here is going to be the main area which is going to find the wall and keep a specific distance from the wall. Whenever there is a wall, this area is going to detect it. Let's say the span is from this point to this point, and it will say that I have an object in the area number 1. As we have discovered in the previous project, we can find any object in a certain area. We can tell area number 1 value is less than 100, less than infinity, less than 100. I've set it to be, if the value of an area is less than 4, there is the wall in that specific area. We have to move the robot in a way whenever the area number 1 has a value less than 4, which means there is a wall, keep the robot moving. We have found the wall. That is the basic concept of following the wall. Now, when we want to keep a specific distance, we have to obtain the value, the minimum value from the area number 1. We will find that value. Let's say it is 2. Okay, it is 2. Well, we assume that we want the robot to be at value number 1.2. We call it to be a set point. I'm using the jargons of PID so things can make sense to you after this course, or if you use PID, it will help. Set point to be 1.2. So 1.2 is actually the desired distance from the robot to the walls. Okay, it is desired distance. It's not the actual. So we will introduce a term named error, in which we are going to say 1.2 minus any value of area number 1. Any detection in the area number 1, that will bring us a value which will be filtered to be the minimum value in the area number 1, and that is going to be subtracted from 1.2, which will tell us about the error. It's like, for example, if you have a friend in the street number 3, you are in the street number 1. What is the error in between you? With respect to the second friend, you are 2 streets away from your friend. So the same case applies here. Error is equal to 1.2 minus minimum error, meaning we want it to be on 1.2, but where the robot is going to be subtracted from 1.2, and error is going to have a value. Let's say the minimum value was 2. The robot was at 2 meters, but we want it to be 1.2 meters. So error becomes 1.8. Oh, sorry, negative of 0.8. Now what we will do is give the 0.8 negative value to angular rotation of the robot. You have to understand this. If your robot is at this point and the distance from the robot to the wall is minus 0.8, the desired position, which is going to be, let's say, this position the robot should be, but the distance from this point to this point is 0.8, not this point, 0.8, and that negative. You want the robot to take a right turn. That's fine. How much degrees of right turn do you want? We are leaving that to an open case, and we are going to say the amount of difference the robot have, meaning the error, we are going to supply it to be the angular rotation of the robot. Okay, meaning robot at this point is going to take a rotation towards the right with 0.8 degrees, not degrees radians, but it is going to take a turn of 0.8. This will solve the problem of keeping a specific distance and following the wall. The second case is very simple. When the robot has a span of this much and there are 3 separate regions, robot is here and there is no wall. Robot has crossed the wall. Okay, what happens? The robot will still moving with the same angular and same velocity, same angular velocity and same linear velocity as it received in the previous iteration. For example, velocity was 1.2 and angular rotation was 0.8 in the last iteration when there was a wall. What will happen? The robot will continuously publishing the message with the previous values. It is dangerous and the robot will keep on doing that, which will cause a failure. This case helps in one condition. That's why I have made it. For example, there is a skip in a wall. Okay, there is a skip in a wall. Then this case helps. Robot keeps on moving. Let's say if there is a skip and there is no angular rotation, what will happen? The robot will keep on moving in a straight line because the previous message was 1.2 velocity only, and the robot will keep on moving, causing the robot to, again, when the next wall comes in its range of laser, it will keep on following that. So that was the main reason of developing case number 2. Case number 3. In case number 3, if this is the span of the laser, we have 3 areas, and there is a wall from this point to this point, and the wall is taking a turn. Now, with the help of case 1 and 2, what will happen? It will keep a specific distance unless there is a wall. Whenever the wall ends, it will keep on following the previous messages. But we want the robot to take a turn. That's our requirement. What we will do is, if A3 and A2 are equal to 100, meaning area number 3 and area number 2 are not hitting the wall. This whole area is not hitting the wall. Only this area number 1 is hitting the wall. Area 1 is, let's say, having a value of 1.2. In this such a case, take a turn. Take a right turn. In specific to our conditions, we have made the robot to follow the wall on the right side. It is not that much robust. We need to add certain conditions to make it follow left or right, both walls. But now only the right side is what the robot is going to follow. Okay. So in such a case, case number 3 is simple. We want to take a turn when the road takes turn. So we check if area 3 and 2 are not there, or they are giving a value infinity or greater than 4. Which means the wall has ended and we have to take a turn. How do we know that? Because the area number 1 is actually on the wall. So in coming 1 or 2 seconds, the wall is going to end. We have to take a turn to keep on following. These are the cases. Let's program them. So you have gone through very difficult scenarios that I explained for wall following, right? Now we are going to take a look into the code, and you will find a lot of things very similar to obstacle avoiding because we are using the same sensor and same way to process the data of the sensors. First, I'm going to run the simulation, take a look on the output, then we will do different stuff. Now, I'm not going to publish the values of velocity. The robot is not going to move, okay? But it will paste the cases and the velocity, angular velocity, so you can understand what is going to happen if we turn on the robot. Now, before running this node, we have to tell the package about this new node that is going to be named as wall following. Package is same. The file, the node script is different, so I'm going to change it to this one, save it. I'm going to perform the call can build of the specific package. I do this mistake every time, I don't know why. ROS2 launch this gazebo simulation, and here ROS2 launch rover and wall following. This follow wall here is not this one because I named it wall following. This is by mistake I compiled earlier. Follow wall, I gave the same name to the obstacle avoiding, but it should have shown wall following. Let's perform the call can build again. And let's ROS2 run rover. What are the available nodes? Wall following is not showing. What is the reason? Follow underscore wall.y is there. Do I have to put comma? Because that seems to be a very silly problem if this is the thing. ROS2 run rover, and what are the available nodes? Oh my god, this comma was the problem. Obviously, if there is a file and there is a second file, how the computer will differentiate? With the help of comma. Okay, makes sense. But that was very silly of me. Now the robot is here. It is not going to move, but it is printing left, mid, right, angular velocity, and the basic condition of moving forward and not having a specific turn or turn coming ahead, not stuff like that. So now what I am going to do is create a wall. I'm going to pause this simulation and let's create a wall with this thing, these cubes. I know it is not an actual wall, but let's create a wall so we can understand the behavior of our robot. Okay, and at this point I'm going to leave the wall right here. So let's see how our robot will react. This is the case, and let's play the simulation. It says 0.24 of angular velocity is applied to the robot, but as our robot cannot rotate, we have not applied the velocities. So I'll apply the velocities and then we'll look into the code. Save it. Okay, I'll close the simulation and perform the stuff again. And call can build stuff. Call can build it. Then run the simulation and then the node, wall following node. if we have a wall, this wall and this wall, again the wall, I'm creating the wall and the robot is moving quite fast. It is following the wall. Let's take a look. If I pause the simulation, so let's bring the robot to a point where simulation is going to say that now start following the wall. Okay, this is the error. The robot is acting on the error. You can see now it is negative and the error is minus 0.14. It is reducing and you can see the robot is coming back to the wall. So it went a little out of the path, a specific distance that is defined. The robot went out of that. Now the command has been sent to take a specific turn. Multiple times the turn command has been sent and the robot is taking turn. Wow, that is awesome. That is actually very awesome. Nice. The robot is taking turn. Which means our code is working fine. The case is that we have to find a basic and take a turn case. So all of them are working. What we are now going to do is take a look on the code and then we'll come back and create a new world. Okay, I'll close this, and let's close this. So in code, first we have the publisher, subscriber, linear velocity, regions defined. Values of region are set to 0 for initially, not causing any issue. You will see there are cases to tell ourselves what is the current state of the robot. Then we'll go into the subscription point where we obtain the laser scan values and we divide into regions. Now this time, as compared to obstacle avoiding, regions are very, very small. Previously we were taking 120 values into a region. Now we are not caring about 300 values. We are leaving them as we don't need them. We have a wall on the right only. So that is why only 60 values are enough to process this wall following behavior. Then this round is applied. Round function is a basic Python function to reduce a lot of values in the decimals to specific only 3-digit values. Okay, so round is applied and I'm going to apply round as well to this angular velocity as well. So only 3-digit values are after decimal are visible. Solves a lot of things for us. Apparently it will be very easy then. Proportional controller is the controller that we discussed, in which we have to calculate the error to, from our desired set point, which is 1.2, and the region 1 distance to our wall. That is going to calculate the error. Then we will define this case in which we have to take care of overshooting angular velocities. If the angular velocity is greater than 1.75 in the negative, when the value is not on any wall, the robot is going to take enormous amount of turns. So that's why I have to limit it and bring it to 1.57 only. And obviously if the wall is on the right side, the values of the distance increase from 1.2, robot is going to take a turn towards the wall. So that is why it is 1.57. Linear and angular velocities are provided. Linear velocity is the constant velocity. Angular velocity here is the value of the error. That's why we are limiting it to 1.57 only. Change in sign of the value is because anti-clockwise rotation is opposite to the wall. Clockwise rotation is towards the wall. So negative sign is rotating towards the wall and we are requiring it to move away from the wall. That's why this error value has not used a negative sign. Okay, in some cases it is required, but for this specific case where we are requiring it to shift its sign, we are applying this limit. Command velocity, for all of the reasons, whenever the first area is on the wall, you are going to apply the proportional controller, and it is known as the basic condition in which you are moving forward. Now whenever there is a case in which region number 3 and region number 2 are not on the wall, meaning there is a turn ahead and robot needs to turn after a certain time, sometime 1 or 2 seconds, we are going to say take a turn, or I'm going to say turn ahead. Turn ahead. Set the linear velocity to double the speed of the constant velocity we set earlier. It was 0.2, now we say 0.5 and take a sharp turn of minus 1.57, which is taking a turn towards the wall. Right turn, negative, clockwise rotation. So that are the linear and angular velocity we discussed in the theoretical portion and we saw in the solution as well. Let's now open up the terminal. We are going to perform the Colton build and I'm going to launch the simulation first. Where is the launch simulation? Let's write it. ROS2 launch rover 2 underscore gazebo launch.py. And I do this every time, I don't know why. Now I'm going to create a wall around the robot. The model that I'm going to be using right now is very interesting model, and that is DRC practice white jersey barrier, and I have orange jersey barrier. These all are downloaded from gazebo simulation models. Okay, and I'm going to create a wall around the robot as no node is running, so it is not going to cause any problem. I'm going to place all of these and create a wall. Now let's bring this robot out of this place and let's run the follow wall behavior. I'm going to set the screen right here and let's run this node of follow wall. Let's see how our robot acts upon it. So our robot is following the wall awesomely. That's great. And now let's move to some serious thing, a car which is going to perform line following with the help of computer vision in ROS. Let's take a look. On the previous projects, I might think that you will be excited for the next one because the difficulty is increasing step by step. This project, previous hybrid model, that is going to be obtained from Gazebo model library, a pre-built model, but you have to understand the flow, how it is built, to make changes in it and to use it for your simulation, right? This is almost, not almost, it is a car, but we will utilize it as a robot. New thing here is this model or all of the Gazebo model in its library, open source library, are going to be following an SDF format, not a URDF, simulation description format. It is more powerful than URDF. Important thing here is Gazebo only accepts SDF. It does not accept URDF. ROS converts URDF into SDF and then sends it to Gazebo. Every model you will be seeing contains this model.config thing and model.stf. But because this is a very complex model, it is containing a lot of new stuff that you might not have come across earlier. First, we'll do it step by step. Prius hybrid model. Okay, the folder that contains all of these. It contains materials and then it contains meshes. Then the model config and the model.stf. These two are the main things. Meshes are the thing that are going to contain the physical bodies, the physical structures, how the robot is looking like. For example, this is a wheel. In physical form, it is just a cylinder as we created for the rover. The body, it is going to be a simple square. Let's say, obviously, in meshes you can see there is an OBJ and an MTL file, which is a very complex 3D model file. But we are just understanding it step by step. In meshes, it contains the physical appearance of the body with plain colors, not with the colors with such gradients and explanation. Those explanations are provided by the material file. Now, this material file here contains some images in its textures folder. These images are actually pasted on the meshes. So if it is a wheel, there is an image pasted on it, on its body, so it looks like a wheel. So first we have to create a mesh, then we have images to paste on it to look it like the real thing. So then it makes sense. Previously in the rover robot, you can see it was looking like a robot, but as there was no image pasted on it or no color properly colored or a texture provided, it was not making that much sense. If we show it to some small kid or any person who is not familiar with robotics, it will say it is a toy or I don't know, but not a robot. So for the previous, there are meshes, and on that meshes, these images, hybrid, interior, hybrid, .png, wheels, 3, all of these images are pasted on that meshes, which makes this car look like a car. So that's what I want to focus on: materials, meshes, and model config and model .htf. In model.config, we have basic things: properties of the package, properties of this model, name of the author, and name of the model. That's it. Real deal is happening inside this model.htf. It's like a file in which everything is imported inside it. Meshes are called in, materials are brought into it, and everything is arranged in a sequential manner so things can make sense. For example, links, joints are defined. With those links and joints, we provide materials and meshes so everything makes sense. That's why this model.htf is the most important file. It contains the summary of all the things in the package of this previous hybrid, and we are going to edit it because we want to add a plugin, a camera plugin into it. That's what we are going to do. Let's jump into it and add this plugin. Okay, I know it was confusing. Everything about gazebo models was confusing. I will show you physically how things work and they will start to make sense. Now, this is a repository of OSRF, Open Source Robotics Foundation. They have gazebo model repository in which all of the gazebo models are present that will be very useful for your future, current or past simulation. Now, I'm going to open up these links, and these links are actually tutorials of how to use these models. Okay, you can also open up these links. I'm first going to clone all of these models. If you know what it is, I'm going to download all of the models into a folder. I'm first going to create a folder in the home directory. I'm going to create a folder named models, and that's it. I'm going inside of this models. There is nothing inside. I'm going to git clone and press enter. It is going to take a lot of time because the size is around about, I don't know, 4 GB or 3 GB, I don't know, or 1 GB, a lot. And all of these gazebo models, all of these models are going to be downloaded in that folder which I created. Now, obviously, I have already downloaded it because I have to create the course in which one of the model is being utilized. So I have already downloaded them. I am going to stop it because I know what I'm doing. You have to download them, open up gazebo. When gazebo is on, go to insert, add a path. In this path, now with the help of a path, you are going inside of where I created the model folder, models. If I press open, what I will get? I get nothing because I stopped the downloading of the models. Here I have multiple models. All of these are extracted from the same repository. The first one is the beer can. I'm going to place the beer can here. You can see this is a beer can and there is an image on it. Okay, let me bring an ambulance. Oh my god, this is an ambulance. That is a proper ambulance. Wow. Okay, I have a Prius hybrid. Okay, this Prius hybrid is also downloaded from the same GitHub repository, and you will add the path of the folder in which all of the gazebo models are there, and then you will press OK, and it will appear here in your gazebo whenever you will open it, not once. And let's say I want to open gas station. Oh my god, proper gas station. Wow, all of these great models can be utilized for awesome simulations. Drone, mobile robots, robotic arms, great simulations can be done. And last one, VRC driving terrain. Let's see what it is. Oh my god, this is something serious. Double pendulum inverted base. That's awesome. I deleted all others, and you can utilize these models and the ones that are provided with the repository into projects, and they will help you a lot. Now our focus is going to be on this previous stuff. Okay, this is going to be the main reason I'm introducing you gazebo models, and they cannot be imported in our ways, obviously, and you will see how we'll work with them, and you will be very interested on things that we will be doing in the future. I will show you one more thing, the files, so you can relate to the theoretical portion. I'll open up the gazebo models, and then I'll not open this file. I will add them to the folder so we can explore them. Gazebo models, home, gazebo models, and okay, these gazebo models, which are practice angle barrier, and I'll show you what these are actually. Insert. This is the orange barrier, this is a white jersey barrier, and these are the barriers that are represented here. And let's take a look inside how they are programmed. Okay, angle barrier, white jersey barrier. There is a mesh folder. There is a 1.4 model STF and 1.7 model STF, I guess, 1.5. So .stf, .config, and meshes. In meshes, that is a Collada file. Collada is actually a 3D mesh file similar to STL, but you can have more properties, more colors, textures for a 3D mesh. Collada files, not the STL. Okay, so you have a mesh file and you have a model. In model.stf, if you open it, it says there is a model static is 2, and this is the URI, and this is the collision. It is very same to the URDF, right? Link. There is no join, but there is a model and there is a URI in which you can provide direct path to the Collada mesh file. Okay, and that's it. But we discussed something very interesting about our previous model, right? I am going to open that. You have brought the previous hybrid model into your gazebo simulation, right? Now we are going to do an interesting thing, is creating a custom world for or a car, whatever we want. I want to show this exercise because creating a simulation is one of the most important tasks a simulating engineer, a robotics engineer who knows about ROS must have. Okay, this practice is very good to build new simulation environment for your robots or create different things into your simulation so you can make robust algorithms close to real-time problems. Okay, now we are going to create a surface that is actually a box, a square box. I've reduced its height so much, you'll see in the SDF file that it looks like a plain thing. Okay, area is so big, but the height is very small, so it looks like a plain thing, but actually it was a box. I reduced its height, and then this was what it was. So this was actually a model, a mesh. What we call a mesh, what we call a model is actually a mesh, and then I pasted an image onto it. I just explained in the previous hybrid thing that this image is going to be pasted on the mesh. We have a mesh, we paste an image on it. So then it looks like this. I created this image and then pasted on this. Now what we have to look into is this whole package. In Road, we have a material which contains a script and textures. Okay, that's it. In model SDF, we bring in the meshes and we paste the textures onto it. Same we did for the previous hybrid model. Now we are going to bring the car at this location and save that to be a specific world, and we don't have to move things around or call the previous hybrid model and road model with different terminals. Make your life easy by creating a world file and launching that world file with single gazebo. That's it. That's what we are going to do. And after that, we are going to talk about the most complex image processing algorithm that I developed on the go for you to understand how to interface ROS with computer vision. Create a package for our previous line following. Okay, previous line following, and everything is going to be ROS to package create, package name, build type, mn, python, dependency. Okay, that's fine. Oh my god, I created it in the models. That my bad. In the source folder of this ROS to workspace, and I have already created. So we'll jump into it. So this is our package in which I've already created launch file, UIDF file, and in the UIDF I have the previous hybrid model, a road, and a world. Okay. These three things, UIDF, I will not be explaining in depth how I created because it will lead into great discussion and great confusion. One thing you should understand, it is basically a simple UIDF. You have to take it like that. In that UIDF, we have model.sdf and meshes and materials. Meshes and materials are none of our concern. Okay, we are not going to be dealing with them. If these links are going to cause problems, if they are not directed to the object they are referring to. For example, if we need the mesh of hybrid.obj, we go into this, we need this. We are going to copy the path and I'm just going to paste it. So if it is on your system or my system, there is going to be a difference in path because the username is always going to be different. Workspace name can be different. So you have to paste these paths of your system to make things work properly. Okay, meshes, and similarly you are going to apply all of them to everywhere where these URI paths are provided. Now, that is one thing about the PS. The second thing is the road. It is same SDF model like a UIDF but a little bit more complex and with more files. There is a material in the road thing. We don't have the mesh. Model.sdf is going to do the thing. Okay, I have provided the URI paths with my system setting, which is not going to work on you because Lukman as a username is present in the path. In your case, it would be different. So you have to paste the path of your system. In this case, road package, I'm going to copy and paste the paths of these folders, scripts and textures. Scripts and textures, I'm going to paste the path of scripts and textures. So you have to copy and paste the path of your system scripts and texture folders. Okay, that's how you have to solve these to make it work. Okay, I cannot provide a general solution. That's what I think. But I'll look into it if I can provide a general solution with the help of providing the links and paths to the package. Let me simplify things for you. You have to just think about only one file, and that is this previous ontrack.world file. In this file, there are a lot of lines, almost 190 number of lines in its code, in its XML code. What it is doing, I have solved it for you. You don't need to think about what the car we are using or what the road we are using to follow the line. I have arranged them and saved them in this file for the gazebo. Okay, that's so simple. As it is a .world file, you just need to run it through gazebo, verbose, and then the path of this file, which is ROS workspace source previous world, and in that we have this previous ontrack.world. You can just run it with this command, providing the address, the path, and the verbose. In this, you can see we have the car, there is a camera on it, and the camera is looking at the line in front of it. Although this line is on a huge road, and the road is ready to follow. I have solved it for you so you don't have to spend time on working on the environment of the simulation. Okay, let me give you some explanation so you can understand and run it on your system. Now, from gazebo models, you have to copy the previous hybrid folder and paste it in the UIDF folder of your package, and then this road folder is already going to be in the repository that I will be provided, although the previous hybrid is also going to be in the repository. Bringing these two packages in our UIDF folder. Okay, then opening up this previous ontrack.world, I am going to search certain things. First, the URI. Whenever I press URI to find it, there is going to be an address to certain thing. For example, scripts folder. I have told you earlier, these paths are going to be different in your case, as this script folder is in Lukman test blender road material script. So you have to do one simple thing for this road.diffuse. You have to open this road folder and copy the path of this script folder and paste here. Again, for the textures, copy the path and paste here. This is going to solve the road importing issue. Okay. Then this URI gazebo material is not going to cause any problem. Again, then next thing is wherever you have this this path in which you are utilizing hybrid.obj, you have to replace it with previous hybrid model, and in that you have meshes. This is the file. You have to copy the path, paste it here in this URI, and save it. For all of you, there is going to be a lot of pasting for this one. I would suggest you to copy this one paste here. In the Visual Studio Code, it is going to mark all of these with the same name, and just paste your address. I'm going to copy path and paste it here and replace all. They all will be replaced. But the problem is I also deleted the URI tag. Okay, so you don't have to do that. You have to take care of the URI as well. That's how you can run this simulation easily by just launching it. I've created a launch.py file in which the command is already written. You just need to launch this car on track.launch.py. Let me show you. ROS2 launch Prius and car on track.launch.py. Things to understand here are in this world.launch file. If I say camera, in camera, although it is not that colorful that it should be, I have added this plugin camera driver and libgazebo camera, which we have installed in our rover robot. All of those settings are added into this Prius car because on the Prius there was no camera. So we first created a link named camera frame in which I generated a box of geometry 0.1, 0.1, 0.1, visually a small box, and then I said this box is the camera and that camera has this plugin in which we have defined camera, libgazebo camera, and all of the values at 640 by 480 is going to be the image size of the frame. Then what we did, we created a joint for this camera frame as we do camera joint. This camera joint is attached to the parent chassis, but this camera frame, if we find it, this camera frame has a specific pose from the chassis, and after a lot of arrangement and hit and try, I saved the file so I don't have to do it again and again. The camera is set at a location, so on the car, and I don't have to do it again. I have saved it and shared with you so you can have a good life. Okay, I ran the launch file and the car is there, the camera is running, we can test certain things. ROS2 topic list, we have the camera topic bandwidth of camera and image raw. How much bandwidth this camera image raw topic is utilizing, and it is utilizing 20.66 MB per second. Oh my god. And now our car is ready for image processing. There is another topic which should be very interesting to you, and I will be using it to drive the car. ROS2 run teleop keyboard and teleop. It is going to be publishing on command velocity. If I drive the car, you can see I can send left, right, forward commands, but not simultaneously with this keyboard. Okay, if I'm making the car move in the forward direction, it cannot be moved simultaneously on the left side or the right side. Okay, this is a problem with the teleop in this functionality. So I have to write a script which will be publishing command velocity, linear and angular both at the same time, and following the line. So we have to discuss a lot about what is going to happen. Okay, let's take a look. Okay, the first script we have is about video saving. We have to capture the video before applying the image processing techniques. Okay, so for that we have just a subscriber class which is going to obtain the frames from the video feed of the camera from the car. Okay, it is a video subscriber. It is obtaining images with the CV2 library, computer vision to open CV2 library. We are going to write the frames at 640 by 480 MJPG and output.avi in the home folder. We will save that video and we will apply image processing techniques, so we don't need to run the simulation again and again. Once we are ready with the image processing with the single frame, then we will reflect it on the simulation. Okay, it's a simple code. It is just converting the images of ROS format image into CV2 acceptable, then writing the frames on the frame. Okay, I'm going to run the simulation in which I have to drive the car. Okay, in this simulation, why the simulation did not run? It said that unable to start server, another gazebo is running. In this scenario, you have to perform kill all GZ server. All of the services of GZ server are going to be killed. Okay, now run the simulation, and I'm going to run the node ROS2 run Prius, not the Prius, ROS2 run teleop keyboard and teleop keyboard. I'll run that before I have to run the video saving node. Okay, ROS2 run Prius and video saver. It is going to display what video it is saving. This is the video feed. I'm going to drive the robot. Oh. So I'm driving the robot. As you can see, it is moving on the screen, and I am going to try to make the car follow the line by manual driving. But the thing is, this video is being continuously saved on my computer. I will complete the lap so I can perform image processing on it. Okay, so I'm driving left and right and trying to make the car complete the track. Although the track is very simple, I have made it very simple to not include the complex cases of computer vision because it's a basic mobile robotics course. I don't want to make it very complex, real world problem. So I think it is enough. We will be extracting a single frame out of it from this video and pre-processing it using OpenCV stuff. Then we'll move towards logic building of line follower. And that's it. Our car has reached the end. I'll stop this video saving node. It has stopped. You can see in the simulation the car will still be moving in the forward direction. Although I can control it, let's stop the car. Let's open up my home folder. And in this home folder, you can see I have an output.avi video, which is the same video which we were streaming while moving the car. Okay, this video has been saved. I will extract a frame out of it by taking a screenshot, and I'll start processing it, and we'll take a look how I'm going to do that. Let's first discuss the 3D. Coming to the last project of this course, line following Prius hybrid car. I know it is funny, but a very interesting project because we are going to go through some very critical computer vision concepts that will help us in future robotics projects. I hope so, and I will be utilizing these in my future courses as well. So the workflow, the base workflow for solving of this computer vision line following problem, I have used first the segmentation, boundary extraction, midpoint extraction control algorithms. This might not make sense right now, but I will go through step by step to make it easy for you to understand. Now this was the image obtained from the camera of our Prius hybrid car. Now what we have to do is to produce this image out of it. it is not a one-step process. It is iterative process, and then at the end of this iterative process, we have to develop the control algorithm, which cannot be directly implemented with any OpenCV function. So computer vision is not a one step or one function or multiple function calls a general solution for everything. You have to take a look on the problem, and you have to adapt. You have to select appropriate functionalities to be applied on the image to obtain your desired result. So in this case, so the first thing is segmentation. Segmentation basically means extracting one desired thing out of multiple or bunch of things. In our case, we have this whole view, which if I explain it in terms of a computer vision engineer or a person who works with images, what he sees is not a whole view. He sees what colors are actually inside of this image. The colors are very easy to extract because this is the one color, it's light gray, this is the second color, and let's say this is a third color, lighter shade of one, and this is the fourth color. Just 4 colors, basic 4 colors, and we can perform the segmentation. In computer vision, segmentation mostly is done on the basis of color. So specifically in this case, the fourth color, the color of the line, which is blue here, although it was red in the model we created because of the HSV conversion, now it is blue. So extraction from the environment is very easy because you can see at the edges the color difference is too much. So what I did, I created 2 levels or 2 intensities of color and the range in between them. It is apparently looking like a blue, but it is an HSV conversion. So it is not 00255 as the example I gave. It was just for your understanding. What I gave was I created a range from light to dark. I just named these 2 ranges. It was from 200, 200, 200. In between these ranges, all of the colors are allowed. Okay. But the colors which are not included in these ranges are going to be deleted, or their pixel value will be converted to 1 or 0, stuff like that. One another conversion was this image was a 3-channel image, meaning one frame had another frame in its background and then another frame in its background of same dimensions. So there were 3 frames for every RGB image. What I did, I converted it into HSV, and then I extracted only single frame with values ranging from one pixel value ranges from 0 to 255. Now 255 is representing 1, 0 is representing black. Okay, giving the values to be allowed and deleting all of the values result into this conversion. And with the line is very apparent, and we have extracted the line from the image. This makes our life so easy because now values are only black or white, 0 or 255. So we can change them, detect them, do processing on them very easily. Let's take a look on how we are going to reach segmentation. First, we need to record the video as well, so we can start processing. It's not like obtaining the image and processing. We have to take care of the dimensions as well. So I will record video, then take an image out of it, and then process it. So let's take a look. The next part is boundary extraction. I called it boundary of the roads, not the whole image, because we are just interested in finding the midpoint of the line. Okay, that is going to be the reference point. So this is a process. So this is the process that I'm going to follow. We want the car to be following this line. Okay, and for each frame that we obtain, and we want this line to be in the mid of car camera angle. Okay, so what we do is to find this midpoint on the line. Now, because of the projective geometry issue, this line, it is of the same width as it is at this point and this point, but the point that is far away from the camera looks a little bit squeezed in its size. That is a projective geometry issue, but we are not going to be dealing with it. We are going to fix an area in which we are going to be doing the image processing. Okay, and that is this square box. It is going to be just one row from the image, but I'm going to draw a square to give you a better understanding. Now we are going to just taking a look into this square. We are interested in finding this very specific point, this green circle, to make the car follow the line and place this line forcefully in the mid of its camera view. So it will be acting as following the line. Our target is to extract the boundaries of this line. This extraction of the boundaries is implemented using Canny edge detector. They are going to give me good results. I applied that, and you can change them, play with them, and find the best the best setting you can get for the Canny edge detector. Simple Canny edge detector, and we got extracted beautiful boundaries. Very easily these boundaries were extracted, no problem at all. Now this result is very ideal, and it was obtained because of very perfect segmentation that we just did. So Canny edge detector is going to be the main thing, and you must keep in mind this square theory that we are just focusing on a specific row of the image. We are not applying midpoint finding of all the rows in the image. What I mean by row is this whole image. This one is just a 2-dimension array of I think 640 by 480 dimension. 480s are the rows and 640 are the column in our case specifically. So what I'm talking about a specific row, I'm talking about, let's say, row number 25 that lies at this point. So this whole row is going to be a fixed row on which line will be detected and midpoints are going to be calculated. So let's take a look on the code how we are going to do that. Here we have a simple script in which we are going to perform basic segmentation, boundary extraction, midpoint, frame, midpoint, and control algorithm. Everything we are going to do that on a single frame first, and then we'll apply on the real previous hybrid car in the gazebo world, right? Here, the important thing to know here is all of these scripts, when I'm processing simple Python scripts with image processing, they are placed in testing scripts, frame, and then applied on the video. Then I will be writing node that will be encompassing all of those strategies, okay? First, you need to understand how I'm going to perform the segmentation, the very basic thing. Okay, importing CV2, importing NumPy, and I am going to read the image. On desktop, I have placed this image.png. I'm going to define the threshold that I want to segment. I will create a mask and I will print this mask. Okay, let's take a look that I have been talking about the segmentation part. I'm going to run it using this Python command, run code, and we will see what segmentation has done. So by just applying this simple process of defining the boundaries, we can see line has been segmented. If I change the values a little bit, not the upper one, the darker ones, 150 to 150, and let's see the difference. And you can see huge difference has been created. So I have checked and thoroughly practiced on the values that should be used in this project. Okay, so you can see a lot of issue can arise because of wrong values. So I'm shifting back to the old values and let's see the segmentation results. Perfect. Because of the great OpenCV, we have very complex concepts and very complex programs installed into this library, and we just need to call the name of the function. Isn't that cool? We are going to apply Canny edge detector to extract the boundaries. Okay, I'll show you the output, then we will have a discussion on it. So Canny edge detector has performed the extraction of the boundaries for the line that we are going to follow. It has performed a perfect job. The issue is the frame is not that much fine, right? I will not crop the frame. Actually, here I crop the frame. I will not be cropping the frame. Let's say this is the case, and I'll show you the output. Image is equal to Canny, and let's see the output. Then we will Canny edge detector applied on the segmented image, and we got this result. Okay, I will leave the cropping part for now, and I will tell you when we will be needing the cropping part. So we have the boundaries. We need to find the midpoint on these boundaries, so we can take action around that point, because we want to keep the midpoint of these lines in the midpoint of the car camera. So we have to find the middle point. How we are going to do that? Let's first understand the theory. Now we are coming to the actual implementation of our control theory, but before that we have to take a look into midpoint extraction. We extracted the boundaries of our line. Now we have to find the middle point of our line, because that is going to be the reference point for our control algorithm. There are two things to look into. First, the midpoint of the frame from which we are going to compare the errors. This one that I highlighted a little bit with the help of changing the values of upper and lower column values of this whole image. So there are 3 pixels having this one value. That is why it is a little bit brighter than the other point, which is this one. And this second one, this one line is the line midpoint. This first one is the frame midpoint. Now frame midpoint calculation is very easy. We know the width of the frame, which is 640. So frame midpoint will be 640 divided by 2. Whenever we are going to take a frame, it is always going to be 320. So pixel number 320, which is going to be the value of the column. So if this is the column of 320, then whenever you have a frame, this column is going to have a value of 1 at a specific row, which is I guess 25. That row in 320 column, the value is going to be 1, which is going to represent the frame midpoint. Now why do we need a frame midpoint? Frame midpoint is actually the midpoint of the camera at a specific row. Now talking about the line midpoint, things are going to get a little bit confusing, because we know that we have fixed the row value. We want the row value to be 160, let's say, which is going to be, let's say this is also 160, and this is the row that we are talking about. We want the frame midpoint and the line midpoint to be detected on only the row number 160. So 160 is fixed. But whenever we perform the detection of edges, the first thing is to detection of the edges in this area, let's say, and this area. Actually, it's not an area, it's series of pixels in a row. Meaning if this is a 2-dimensional array, this whole line, which is going to be 0, 0, 0, 255, and 255. So there are 2 values which are white pixels, and the other 3 are black pixels, 0. So there is a 1 row. The problem is when I'm going to apply a search for the white pixels, sometimes we will obtain 2 values, ideally speaking, one from this point number 1, and let's say point number A and point number B, 2 values. One is going to be, let's say, 40, the second is going to be 120. So which is obvious, this one is from point A and this one is from point B. The problem here is, multi-value problem is, sometimes we will get 3 values, and those 3 are very confusing, because it might be 40, 41 and 120, or they can be 40, 120 and 121. Now if we apply the same technique of processing for 2 values and 3 values, same technique, things are going to get bad results, because the first value of 2 value case is 40, the first point, and the second value of the 2 value case is the next point on the next boundary, here. The first is here at point A, the second is point B from the next line. But in the 3 value case, the first value is from point A and the second value is also from point B. It is a little bit, it is a next value, but it is not representing the second line. So this is the problem, and vice versa. The first might be A and the second might be B, and the third is also might be B. This second case can give you good results, but this first case in the third case, sub case, in the third value case, the first case is going to cause problem if we deal it the same way as we do it for the second problem. So we have to find a solution for that. Now there is also another case, 4 value case. Can you believe it? 40, 41, 120, 121. Meaning there are 2 points found on A and 2 points found on B. Ideally, what we need, 1 point from this and second point from this. And there was a time when I found a 5 value. I said, okay, this is getting worse. I have to perform again a better solution for segmentation, but I took care of it with a simple solution. We have to crop the image. We don't have to look into far ahead of the image. We have to just crop the image to solve the problem, and there should not be too much bend in the image. Okay, that's how I solved this 5 value problem. 2, 3 and 4 can be adjusted as you are going to see in the code. Let's shift to it. If I run this code in which I have set a condition that is saying in the whole image, there is a whole image, and I have fixed a column that is from upside, and if there is any value in the rows, set those values to be 255. I might be saying rows and columns in opposite, but let's take a look. We are going to be saving the file, and I want you to print the edges. Let's see. So what is happening? Is there any output? Yes, there is an output. You can see there are numerous values printed. What they mean? You know, the dimension of this image is 640 in this direction, horizontal, and vertically it's 480, as far as I remember, because I recorded the video in this format. Now 640 by 480, 640 in horizontal. I want a value from this specific point, and I want all of the values around. Now what happens is it is printing everywhere where it is stopped. Okay, let's run it again. It prints all of the values where it finds one value on the specific row that I have defined. Problem here is, in the desired condition, what I want, as I discussed, I want one value on the left and one value on the right, but it is giving me these much numerous values, so I can't process it. That's why I have to crop the image to a specific area of interest, which is known as ROI. Let's do it on the go. If I am going to uncomment it, and let's delete this, and I am going to say 150. Okay, let's see what happens. I'm going to run it, and the image has been cropped, but the image is cropped from the bottom. I want the image has been cropped from the bottom. I want it to be cropped and deleted from the upper side. We want the bottom side. Okay, so what I will do, let me set it to be 100, and I think everything should be fine. Let's run it and check if we have region of interest. Yes, we have a great region of interest. No few further lines and no lines, no, not a curve of the car. So this is our region of interest, and we will be focusing on this portion only. Now, what we were doing, we were finding the midpoints. This was just the cropping that we should have done earlier. Now I am going to find the edges. I'm going to run this command and find two values out of these, one from this line and second from this line, ideally speaking. Let's take a look. And we have just two values, 168 and 637 from these two lines. Okay, that's fine. Two edges have been found. What we have to do is to apply only the division rule, which will bring us to the point where we get the midpoint. So let's run it and see what output we get. And this small point is the middle point of this line. Okay, and this is known as the set point in this condition. We want the car to be following this point. Okay, following this line. Let's take a look how I have done. There are certain conditions that I described. In some cases, there were 3 to 4 values obtained on this sides. For example, 1 and 2 here, and as I have explained in the theory portion, the conditions for if we have 4 values and if we have 3 values, and the condition to check if the value is adjacent or it is from the next line of interest. So we have subtracted them, and if check if the values are greater than 5 or not, then we have assigned them. I have commented some examples so you can read the code and understand what the case it was according to the theory. Now, simply midpoint, and I have set the value of that specific pixel to be 1. Keeping in mind, I have selected a specific row of value 160. This must be kept in mind, and for your information, the pixels of the frame are not 640 by 480. As you can see, some are going 430 and some are going around 600. So the image actually in the video is 640 by 480. For processing, we are just doing that, and you can crop it and make it to your desired image frame width and height, as we will be doing that. The next thing is frame midpoint. It is an easy task. I will run it with the controller. Let me run it first. Okay, I will not run this command, and fimage actually is not defined. Self protection is defined. Self protection is not defined. Okay, let's say the control algorithm is not working right now. We are just going to print things. We'll add it, which is going to set the values, and let's take a look. I'll explain it what it means. Let me first show you the output of it. Let's run it, and you can see the frame midpoint is this point, and it is a little bit off because of the dimension is not right for this image. We'll apply on the ROS video specifically. We know the width and height. Then the frame midpoint will be exactly on the point where it should be. The error is going to be calculated between these 2 points. Let's first understand the control algorithm, and we'll come back to this one. Coming to the last part of this line following algorithm building project of Prius hybrid, control algorithm that is going to control the car and force it to go back to the center of the line. Now we have this small dot as center of the line. The second point, which is a little bit darker because we added adjacent pixels value to be 1, this is the frame midpoint and line midpoint. What we did is apply the proportional controller. In this controller, we found first the error, which is frame midpoint minus line midpoint, and very simple conditions are applied. If error is greater than 0, then it is left. Meaning, if frame midpoint is greater in value, or frame midpoint is greater in value, the value will be greater than 0, so turn left. And if error is less than 0, then turn right. Now, how do I know that? In this specific case, right here, the value of the row starts from this point. At this point, it is 0. So anything that comes first have a small value. So this frame midpoint is having a value of, I'm not giving an exact value, but I know the frame midpoint value here is less than the line midpoint. So if it is 155 frame midpoint, the line midpoint is going to have 160. So the error is less than 0 because it is minus 5. So we have to take a right turn. And you can see by observing simply, you can see this frame midpoint needs to take a right turn to make the line in the mid of the camera and make the car follow the line perfectly. And similarly, in this case, in which the line is a little bit on the left, and we want the frame midpoint to push the car to take a turn and bring the line in the middle of the frame, meaning middle of the camera of the car. So that is how things are going to work. And this is a basic theory of line following Prius hybrid car in raw simulation using Gazebo. Let's implement this last thing, and then we'll move to a turtle bot. Okay, now this is the last portion in which I am going to explain you complete node of line following, and it is very, very, very interesting. We have imported all of the libraries. We need computer vision, CV2, we need NumPy, we need CV Bridge to convert computer vision to libraries into ROS base, and image of ROS base message for driving the car, and CV Bridge specifically I've told you. We need a subscriber to get the image, we need a bridge object, we need a publisher to publish the command velocities to drive the car. Then we create some global variables. That's fine. Now the publisher is actually a very simple stuff. Okay, we have defined the velocity of the car after computing on the images, applying the computer vision technique for line detection and extraction that we have discussed earlier. We are just going to find the error from the midpoint to the frame midpoint, line midpoint, and frame midpoint, and then we will decide the error, and that error is going to be given to the angular velocity of the command velocity message that is going to drive the robot. And after publishing, that's how it is going to be. The subscriber is going to make us revise certain things: obtaining the frame, applying segmentation, mask, extracting the boundaries, applying the cropping as desired, finding the line midpoints. Then we apply the cases to edges. We only need 2. If we obtain 4, 3, 5, we'll reduce them to 2. After obtaining those 2 values of the lines from A line and B line, we are going to find the midpoint of the midpoint of the lines, and then we'll find the midpoint of the frames, then calculating the error and applying control algorithm, which is a very simple proportional controller by multiplying the proportional constant 1, velocity and angular velocity, the linear velocity and angular velocity provided to the car after calculating the error. I have written this line to print out what direction the car needs to move so it follows the line perfectly. Okay, let's run this code, but before that we need to launch ROS to launch Prius car on track. We'll bring the car on the track and open up a new terminal, ROS2, run, previous model, and line following. Video saver, lane following, line, we need a line following. Let's run it and see what happens. So the car has started to move and it is sort of playing with the midpoint. The more brighter point is the frame midpoint, okay? And the lighter one is the line's midpoint. And you can see the brighter one is trying to catch the light midpoint of the line. Now is coming the important and interesting part. Sort of a turn is going on with the car. The car's action is a little bit jerky, but still it is following the line, and so awesome. Wow. Line has been perfectly followed by the Prius hybrid using this technique of line following. But the thing is, there was not a one function solution or one approach solution. We have to divide the process. We have to solve step by step segmentation, line extraction, line following. All of this has to be done in sequence to perform this awesome behavior. So that was it for this course. Now what I'm going to do is to explain you certain things, how you can learn more about ROS2 from commercial projects, okay? So what I'm going to do is tell you a little bit about a robot. If you don't know, Turtlebot 3. If I just type Turtlebot 3, okay, simulation GitHub, it got open because I searched a lot about this. If I just type Turtlebot 3, and you can see Turtlebot 3 robot is a manual on images. You can see great robot, great support, great people provided, awesome support. This page here, right here, emanualrobotics.com. It is the best thing to learn ROS when you are ready after this course. Obviously, you understand the basic, and you can, I think, start with a free course as well. You can come to this point and you can take a look on what these people are going to tell you. For example, I go into this run slam mode, and here I select my Foxy tab, and that is built for Foxy. It tells you about launching different nodes, performing certain things, and awesome stuff. Very awesome thing. You can also run for your ROS1 melodic noitic, dashing is ROS2 noitic as well. There is also detailed documentation about navigation, simulation, manipulation, and stuff like that. Open manipulator is also provided. Machine learning, autonomous driving, everything is here. You can check those things and get started. For example, we want to know about autonomous driving, okay? And they say that Turtlebot 3 Auto Race 2020, you need to download it. I'm not going to download it. I'm going to open it on the website of GitHub, and I can get into these folders and find a lot of useful stuff. And I learned a lot from Turtlebot 3. Hats off to these awesome people. It says auto race camera. It's calibration nodes and stuff. I want to take a look into what is inside it. What my interest would be models of robots and the simulation environment. Can I find them? If I go into multiple folders, I might be able to extract the source codes and the simulation environment for Gazebo as well. For example, launch files and launch file. If I run it, I can read these launch files because I've spent a lot of time on ROS1. I can understand what they're saying and what files they are calling. Okay. The second repository of the same robot is Turtlebot 3 simulation. If I open this Turtlebot 3 Gazebo here, I have this models, I have this launch files, and the worlds. Talking about the worlds, we have utilized the Prius car on track launch file, which was running a Prius and road world. You can open up this world, Turtlebot 3 world, with the same code, same syntax, because both are world files, the SDF format. They are going to utilize models and stuff like that. So things are going to start making sense for you by exploring these commercial quality products, okay? And this world can be downloaded, and you can run it after installing this dependency of model Turtlebot 3. If we talk about the models, what models do we have? For this Turtlebot 3 Waffle.py version of Turtlebot 3, we have model.stf, we have config, and this simple version. I think you understand that .stf is going to contain the main deal, inertial properties for the link, and visual properties, collision properties. If I go down, we have image joint, LiDAR joints, and all of that stuff that you must be able to understand. One thing that I have not done in this course is to provide mesh files directly for the rover robot, or my custom build mesh files for my robot. I have not done it yet. I will be doing in the future courses, but you can try and make your custom 3D model robot in CAD software and bring them into ROS. That would be awesome. That Turtlebot 3 had done. It has provided the Collada files and brought them into simulation. You can download it according to this simulation, according to this e-manual of Robotis for Turtlebot 3, and you can learn a lot. Okay, that was all about Turtlebot 3. And if I open up the terminal, and I want you to install this package, sudo apt get install ROS Foxy Gazebo plugins. Okay, these Gazebo plugins are going to install a lot of plugins, around about 20 plugins that are going to contain examples for you to understand how you can install Gazebo plugins for your robots. Let me show you an example. If I run that Gazebo, I know where Gazebo plugins are installed, so I'm going to give the direct address to the worlds. You will love them really. CD, OPT, ROS, share, Foxy, share. Now in the share folder, we have all of the basic packages of ROS installed. Okay, if I press double tab, it says 274 possibilities. I don't want all of these. I want Gazebo related possibilities. So Gazebo message, Gazebo plugins. This package is what I'm interested in. Okay, Gazebo plugins. Go into it, and if I press tab, I think worlds folder, and that's it. This is the path to a place where you can learn too much. For example, if I list it, there are a lot of things. Gazebo ROS Ackerman drive tutorial. Let me show you one. Gazebo verbos, and any one of this world. Let's say, what should I say? Gazebo ROS. Skid steering, is there a skid steering? Yes, there is a skid steering. And you know what will pop up for skid steering example? This funny robot. And if you open up the code of these files, you will find a lot of more detail. And how you are going to do that, let me show you that. Gazebo plugins GitHub. So let's find it. I think it is not there. So here we are. It is noitic development. We are developing on ROS2, so we have to select for Foxy specifically. We select Foxy here, and then we'll go into Gazebo plugins, and then worlds, and all of these files are available that we were looking into our install package. And what I just want to show you, what we opened was skid steering, right? And if we look into its code, First thing they said, you can try sending this to drive the robot. Let's try it. Open up another terminal, pasting it and running it. Let's see if it moves. Yes, it is moving. I don't know what is the shape saying. I don't like it, by the way, but it is working. It is a skate steering. I don't know how to drive it, but if I go into the code that is provided in this .word file of this gazebo plugins and a lot of other plugins as well, they have explained a lot of things to work with this SDF file, this long word file. So in a nutshell, you can learn a lot from the online available things, and that is the power of ROS. This brings me to the point, and I have to say it, this is the end of the course. I will be sharing some free resources with you in the next video and saying you goodbye from this course, and obviously inviting you to the next course that I will be creating. Take care.